Our sun is quite large. It is so large that you could fit nearly 1,000,000 Earths within. However, how does our living ball of compare to some of the world's titans, plasma? When you give it any thought, the scale of it all becomes nearly impossible to understand. Some stars are 1,000 times bigger than the sun. Others' suns are millions of times bigger than ours, the largest being almost 10 billion times larger. Greater than 1,000,000 times the size of the sun, several times the size of our light blue. Please, returning to the topic at hand, we're investigating some of the biggest stars in the cosmos and whether they actually ought to exist. Hello and welcome to KYC News. Please don't forget to subscribe and hit the bell icon. A star's photosphere is used by astronomers to measure it, or the star's outer surface, from whence light emanates. They measure the star's size in relation to solar radii, is a concept used to describe our own sun. Therefore, if your star has a radius of 10 solar radii, that would result in a neat alignment of 10 suns. Based on theoretical theories, its diameter star should reach its maximum size around 1,500 solar radii. Enormously massive stars with a large radius, if you compare by a distance of about 648 million miles volume, a star that has a volume of 800 million suns large. But we've discovered a few stars that are, even until recently, astronomers believed bigger. Scuti was the biggest star that had been seen. The star Scuti is located in the constellation Scutum. The Milky Way galaxy cannot be seen with the naked eye, due to its location in a region of the galaxy whose stars are obscured by the Milky Way's light, but scientists discovered it in 1860 and it has grown to be extremely large. Around 10,000 Scuti was believed to be light years away from Earth. To have a solar sphere with a radius of 1,700 and approximately 200 is the margin of error, which indicates you could fit 5 billion suns inside of it. Scuti is greater in circumference than the Jupiter's orbit around the sun is so extensive that an imaginary object moving at the speed of it would take light 7 hours to complete the circuit. If Scuti had an orbiting planet, it would have been more than 600 astronomical units. From the 1 astronomical unit is the distance from the enormous sun, approximately 93 million kilometers separate Earth from our sun. Just how far are 600 astronomical miles? Pluto is only 39 astronomical units away. Yet latest readings show that it is distant from the sun. Gaia Space Telescope has tossed a wet towel cloak on the excitement following the Scuti revelation, the possibility that it is only 5,000 light years away, resulting in a 755 kilometer solar radius. Still enormous, but not nearly as large as Stephenson 2-18. Stephenson 2-18 was crowned as the best in 2021. The biggest known star, comparable to Stephenson 2-18, although it's in the constellation Scutum instead, a great distance distant, roughly 19,000 light years. It is a part of a collection of objects far from Earth. The region termed contains 26 supermassive stars. Stephenson 2, meanwhile, is more of a brighter, larger, and unlike any of its siblings, it is an oddity. If Stephenson 2-18's distance is correct, it means that it weighs in at a massive 2,150 solar 10 billion times the volume of the radius. Our sun's diameter would be larger and extend further than an object's orbit around the sun, that of Saturn. 9 years to travel at the speed of light hours to complete a full circle around Stephenson 2-18. In addition to Stephenson 2-18 is, if this is accurate, it's still developing and young. Then it can be approaching transition. An exceptionally bright blue variable star, when a certain kind of hypermassive star, which is rare, superbehemoth, sheds its outer layers to become into extremely erratic and changeable in brightness, yet is more brilliant than a supernova. Giant explosions occur in blue variable stars that look like little supernovas and are referred to as supernova imposters. Moreover, Stephenson 2-18 might transform into a Wolf ray. Currently, these stars have lost all of their emit around 10 suns worth of material and hydrogen. As their cores disintegrate once per million years, they can compress or explode into supernovae depending on their masses. Black holes can be explored further. One of Stephenson's more perplexing characteristics, its powerful luminosity, which is 2-18, is 440,000 times. This is a number that was brighter than the sun based on the Eddington theory, considered to be impossible 320,000 times the maximum allowable luminance. The Eddington limit for the sun is essentially the brightest or most luminescent a star achieved by balancing itself without disintegrating in a circumstance of hydrostatic balance between the radiation's external force and internal force. How is it possible that Stephenson 2-18 is as strong as it is? Huge and so dazzling. Describe the mathematics in some way. Cosmological models. Before we respond, let's observe how it initially becomes so large. Clouds of interplanetary dust give birth to stars. It may have a diameter of hundreds of light years. These clouds are first chilly, diffuse, and over time primarily of hydrogen and helium. As more and more atoms are drawn together by gravity in the cloud, increasing its bulk, when a cloud grows large enough, it transforms. The gravitational collapse is unstable. As the cloud dissipates, the temperature increases. As the atoms of hydrogen and helium move closer together, more mass inside the cloud's core indicates more gravity that draws in more and more through a process known as accretion. Cosmic material. Usually when a protostar starts to form, a cloud collapses. To thousands to hundreds of thousands of stars, almost simultaneous formation and embedding stellar clusters are essentially a collection of stars. They were encircled by the ruins of their mother cloud. Several circumstances can result in the birth caused by gravitational collapse of stars. Hydrogen and helium alone are insufficient to when a cloud is collapsed. There must be signs of these other, heavier elements may originate from the relics of older, supernova-killed stars and launch shock material into the sky at high altitude. Whole galaxies colliding at high speeds. Massive amounts of energy cause starburst forms as each galaxy's gas clouds are gigantic jets pressed up against one another. Additionally, black holes have been recommended as energizing star development, supplying the stellar system with energy whatever the cloud and causing its collapse, cause the atoms in the body reach a specific point when the condensing cloud has compressed so much that their electrons are taken away, leaving exposed nuclei and strongly charged ions. The intense heat and quick compression of these exposed helium and hydrogen nuclei causes the nuclear fusion that produces a star. Once the star has ceased, a fusion plasma generator, nuclear fusion, as well as collapse the plasma of the atoms in its center, is pulsing. Star begins to grow, but the growth is the gravitational pull of the stars, and the anhydrostatic equilibrium, plasma, is retracted. Is accomplished, as we previously indicated, where the star's radiation pressure and gravity are equal. Consequently, the star becomes more or less steady. Subsequently, a continual series keeps the stars alive. Of explosions as hydrogen and helium are combined, a stunning 620 million particles are fused in our sun per second, converting tons of hydrogen into helium every second. But how can a celebrity grow to be one of the biggest? The size and nature of the gas are considerations. Initial size of the star's forming cloud, and once a protostar has stabilized, it becomes the protostar. Become what are referred to as main sequence stars these days. The size of stars can vary from 1 to 8 times that of the sun. Over the course of a star's existence, our sun burns. Through the internal fusion of hydrogen to helium portion of the larger main sequence's core due to stars burning, this process proceeds more quickly. In smaller stars, their hydrogen moves more quickly. It proceeds more slowly, taking somewhere between between a few million and a few billion years to use up all of the hydrogen stored inside of it. Moment a star exhausts its hydrogen fuel, it has a lot of helium left behind after taking higher temperatures and a lot more energy dispersed, something the star lacks. Therefore the star starts in fact contract as it reaches hydrostatic equilibrium, is knocked off as gravity begins to draw, and when it does, the core becomes warm. Once again, when more material is drawn and more hydrogen is drawn in near the core and envelopes the helium in a shell center where fusion resumes, followed by a process as the inner core, the mirror principle, takes place. The layers outside compress within the shell widens and the star multiplies larger, which causes the core to heat up. sufficient to begin fusing helium with carbon. When this occurs, a tremendous quantity of energy is after the star was freed. It grew into a crimson behemoth. This is what our sun will someday experience. However, given that the sun is merely a moderately sized star, would become a red giant and eject the majority of its stars. A white dwarf by compressing all of its gas after that. At least 8 times larger stars than our sun can move through a further stage where if they have enough mass, they can grow to be supergiants. A big star's carbon core can start to fuse. Heavier elements, such as oxygen, sulfur, and silicon, produces additional energy that powers an additional growth, producing some of the largest stars like Stephenson exist in the universe 2 to 18. How therefore does a star like Stephenson 2 to 18 come to be? If the object's brightness and size seem to exceed boundaries suggested by the mathematical Eddington luminosity limit equations, the first being stellar evolutionary theory, the simplest response we could have received is incorrect measurements were used to calculate the distance. Additionally, a star's brightness is quite complex. 2 preliminary steps are needed to determine a star's radius. Its angular diameter, which is observed the size that it appears to be from Earth, and the actual. It is simple to calculate the angular diameter from Earth. Sufficient to calculate, but establishing precisely exactly how far a star is from the Earth extremely challenging. Interstellar radiation gains the star's brightness as it approaches us. Numerous huge celebrities, including UY Scuti and Stephenson variable, varying luminosities are present in 2 to 18. Release a great deal of gas, toughening them to observe the light coming from the Milky Way galaxy. Also makes several stars invisible once more. Close stars are difficult to view, therefore astronomers utilized using a technique known as parallax to determine a star's. How parallax works in relation to distance from the Earth. Suppose you're outside admiring some trees. When viewing distant mountains from a car's side window, you will observe as it travels down the road that as you pass the trees, they appear to be moving more quickly. Then the same mountains in the distance nearby stars appear to move as something happens in the sky. Quicker over the period of a year across the sky. By measuring the location of a star once 6 months later, take another measurement to, based on the star's angle, determine the distance to it. However, precise parallax measurements are limited. Up to around 400 light years away. For stars that are further away, astronomers have employed we can estimate the spectral information of the stars to reuse parallax to identify 2 beneficial components. Calculate the solar radius luminosity of a far-off star and temperature tend to be around supergiants to be cooler and reddish in color, and astronomers projected using such data to stars that are further away, like Stephenson 2 to 18. Simply put, it isn't entirely accurate, but it's still a fairly good method. Consequently, if the data are accurate, our model of the information on star evolution seems to be lacking. To understand why these supergiant stars are so bright could be connected to the phenomena known as going the Eddington limit is super Eddington's upper bound. Luminosity a star can reach when there is a balance, hydrostatic equilibrium occurs. Internal pressure that emanates from it and the force of gravity pulling on it. If you can think of any greater star from the outside, more than 1,500 solar radii should immediately explode into a. But Stephenson 2 to 18 with its 2,150 solar-powered radii hasn't, yet a star can exist in a number of ways. Can possibly become even more super Eddington while maintaining its shape. The lightness. The first is a concept known as atmospheric porosity. Visualizes the star's atmosphere as having areas of high density surrounded by areas of low density. Essentially, this would contain the mass. Star loss in the outer layers, intensifying the illumination, while the star's inner, denser core is still present. Another justification relates to what are said to as photon bubbles are accelerated by radiation. They are instability in the stellar atmosphere, hypothesized to form within a star with a lot of radiation when the radiation pressure exceeds its. Basically, these bubbles are caused by internal gas pressure, capable of moving photons and light more quickly. Huge stars to move at faster and more efficient rates. Glow brighter, so much is up in the air. When it comes to the biggest stars in the universe currently, Stephenson 2 to 18 wins. However, as we improve satellite technology and can more precisely and farther into the universe, what we might discover appears to have no boundaries. Thank you for watching.
Yeah.